Do you know what is minimum potential energy principle? Have you understood minimum potential energy principle completely? If not, let us see. So minimum potential energy principle, to explain, I'll just consider one simple example. Let us say there is an axially loaded bar. Okay, so it has got axial load P at the free end, and one end is fixed. So let us say end A, end B. Okay, yeah. So for this particular load, I'll try draw the deformation of this bar. For example, say this is the original position of the bar. Let us say this bar elongates this much. So I don't know the exact value. Okay, this is a possible deformation value. Okay, this may be the another deformation value possible because you don't know the value, right? So yeah, this is another deformation value possible. So likewise, you have infinite number of possible deformations for this problem. Okay, what exactly is the value that it is going to deform the delta? We don't know. Okay, but all these deformations that I have drawn, like 1, 2, 3, 4, 5, 6, any number, are satisfying boundary conditions. Boundary condition means you see the left end is fixed, so no deformation, and all other points are free to deform. So all these deformable shapes that I have drawn are satisfying boundary conditions, and the deformation that I have drawn is compatible. Okay, compatible. See, if you draw this deformation like bending, like, okay, it's if it is bending, if you draw, it is not going to bend because you are pulling it, so it has to elongate. So that is what is called compatibility. It can't be twisted because of this force. Okay, it has to only elongate because you are pulling it. Okay, so twisting or bending is not a possible configuration. That is what is called compatibility. Okay, right. So all these deformation that I have drawn are satisfying this boundary condition and satisfying the compatibility conditions. Okay, then the principle says, okay, the configuration which satisfies equilibrium. Okay, the configuration which satisfies equilibrium will have minimum potential energy. Okay, minimum potential energy. That is what is called minimum potential energy principle. Okay, so out of all these configurations, only one configuration will satisfy equilibrium condition or equilibrium equation. That will have minimum potential energy. Okay, so when you apply this principle, okay, now that you have understood what is the principle, so minimum potential energy principle means for a given problem, for a given structural system, of all configurations which satisfy boundary conditions, compatibility conditions, there will be only one configuration which satisfy equilibrium also, that will have minimum potential energy. Okay. Yeah. So when you want to apply this, okay, we will apply now in the reverse manner. Like when you apply this principle, we write potential energy of the system, total potential energy of the system. Okay. Then we search for where this is going to be minimum. Okay. So minimum means I take it as 0. So that will give you the unknown value of displacement. Okay. If your problem is involving displacement. Okay. So for example, yeah, if you think in the reverse way, if potential energy is minimum, if pi is minimum, then what you are getting is an equilibrium condition. Okay. So which means I will get equilibrium equation. Okay. So for any system, if you apply potential energy is equal to minimum condition, that will generate an equilibrium equation. Okay. So let us check this for this given problem. Same, consider the same problem. For example, the axially loaded bar itself. Okay. But not the deformable body. Consider this as a rigid body. I'll try go back to the mechanics, engineering mechanics. Okay, let us say this is a rigid body, means no deformation. Rigid bodies don't deform. Okay, yeah. For this, you apply this principle. Okay, so the total potential energy is equal to, okay, internal energy plus external work done. Okay. So internal energy, because this is rigid body, internal energy is 0. Work done is force into the displacement. For example, just imagine this bar is displaced by an amount of u, let us say. Okay. This bar is displaced by u amount from this point to this point is u. Okay. So as you remove the fixity here, you will have a reaction. Okay. So now u is 0. So I need to write w. Okay. So this has to be 0. Okay. So I got a condition that total work done shall be equal to 0. So now I'll write the work done from this. So force and displacement are in the same direction. So it is positive. Here force is towards left, but the displacement is towards right. So minus R into U is equal to 0. This is total work done. So U common, P minus R into U is equal to 0. So as U can't be 0, okay, this has to be 0. P minus R is equal to 0. So which means P is equal to R. So this is what you get from the equilibrium equation. This is what is the equilibrium equation. Sum of x forces is 0. Okay. So the pi minimum condition, okay, pi is equal to 0 condition, you are applying and you are getting equilibrium equation. So that is what is the principle in the other way says. Okay. So this is the clear understanding of the minimum potential energy principle. Okay. So I repeat the principle once again. Of all configurations that a system can have which satisfy boundary condition and compatibility condition, okay, the condition, the configuration which satisfy equilibrium also will have minimum potential energy. Okay, that is a principle in its form. But when you apply, you apply in a reverse way. Okay, we apply pi is minimum condition, then we get the equations to solve. Okay, those are the equations that you get by applying this condition are equilibrium equations. Okay, so if you are asked for what are the equations that you generate by applying this condition, minimum potential energy condition, they are nothing but equilibrium equations. Okay, yeah, thank you. We'll see you in the next session.